Today we're going to talk about another non-parametric test. This one is for paired data, and it's called the sign test. We'll start with an example. Suppose that a company that produces sunscreen decides to test the effectiveness of a newly developed formula. An experiment is performed with 25 subjects, each of whom has the old formula applied to the left arm and the new formula applied to the right arm. Each person is exposed to 1 hour of sun, and the degree of redness on each arm is compared. And here are the results. For 14 people, the left arm was more red than the right arm. For 6 people, the right arm was more red than the left arm. For 5 people, there was no noticeable difference. We ask, can we conclude that the new formula is more effective than the old formula? Well, there's some issues here. There's no numerical scale that measures the degree of redness. All we're doing is checking each arm and deciding which one is more red. Therefore, the data are certainly not going to be normally distributed. So we can't use something like a paired t-test. Well, let's look at what the features are of the sign test. The sign test happens to work well for both cardinal and ordinal data. Cardinal data being numerical values. And ordinal data being data where order matters, but specific values do not. In the case of our sunscreen experiment, right, the order matters. Which arm is more red, the left arm or the right arm? But there are no numerical values. Okay, this test is going to be non-parametric, so it's not going to estimate a parameter. And this test is going to require paired data, like our left and right arms from the same subject. You'll see some instructions for applying the sign test below, but I think it'll be easier if we just look at the example. So for our sunscreen example, we're going to have two hypotheses. There's no difference between the two formulas, and there is a difference between the two formulas. Instead of the two formulas, you could also say there's no difference between the degree of redness or you could say that there is a difference for the degree of redness. Okay. The important values for this test are going to be two numbers called n plus, the number of positive differences. In this case, that is 14. That is where the left arm is more red than the right arm. The number of negative differences, that's going to be 6. That's where the right arm is redder than the left arm. And the number of non-zero differences, which in this case is 20. So we're going to ignore the 5 subjects who had their left arm and their right arm have no noticeable difference in redness. And we're just going to focus on the 20 subjects for whom we could see that there was a difference. Now we have to define the test statistic for this test, and it's very simple. It is the larger of n plus and n minus. So the test statistic in this case is 14, and the test statistic is called B sub s. Now we have to find the p-value. And in order to do that, we're going to look at the chart for the sign test. So coming down to the chart for the sign test, we're going to look at 20 subjects for whom we saw that there was a difference. So n sub d is 20. And we saw that 14 of those went one direction. 14 of them had the left arm redder than the right arm. And so you can see next to 14 is the p-value of 0.115. So corresponding to our test statistic of 14 and our number of data points, 20, then we see our p-value is going to be 0.115. And therefore, we cannot reject the null hypothesis. We cannot say that there's a statistical difference between the formula, the old formula on the left arm, and the new formula on the right arm. Now that seems like a very simple test, but you might be asking yourself, where did this mysterious p-value come from? Well, the p-value, which we remember, is the probability that you reject the null hypothesis, given that it's true. In this case, it's the probability that the test statistic B sub s is bigger than or equal to k, given that the events that the differences are greater than 0 or the differences are less than 0 are equally likely. And you can calculate this using the binomial distribution. So let's see how that works. So for our test statistic, we had B sub s is 14. Okay, so our p-value is going to be the probability that B sub s, our test statistic, is bigger than or equal to 14. Now there are two ways that we can get a test statistic that's bigger than or equal to 14. The first way is that n plus is bigger than or equal to 14. And the other way that we could get that is that n plus is less than or equal to 6, meaning that n minus was bigger than or equal to 14. Now, both of these probabilities are going to be the same, so we're going to look at that as being 2 times the probability that n plus is greater or less than or equal to 6. So that's 2 times, and now we're going to apply the binomial distribution, the sum from k equals 0 to 6 of 20 choose k times 0.5 to the k times 0.5 to the 20 minus k. So here, if n plus is less than or equal to 6, we're summing up all the possibilities that n plus could be 0, 1, 2, 3, 4, 5, and 6. Each one of those, the probabilities, are found using the binomial distribution. We can simplify that a little bit. This is a sum from k equals 0 to 6 of 20 choose k times 0.5 to the 20th power. But this sum is still a fairly tedious calculation. We can write it out and find out that the p-value is 0.115, but it's a little bit easier if we just refer to table 7 instead. One important note before we finish is that the sign test chooses to ignore samples where the differences are 0. And that's something to think about, whether that is something we should be doing or not. And that ends our lesson on the sign test.